Swayam Prabha. Digital India. Educated India.
Now, in continuation of division algorithm, we have to follow the next module is arithmetic function. So, it is very necessity to understand the arithmetic function, and then let us start with the multiplicative function. First definition says that f is called arithmetic function or number theoretic function if it assigns to each positive integer n a unique real number or complex number f of n. Typically, an arithmetic function is a real valued function and a domain set of positive integers. So, that is the meaning of multiplicative functions based on the number theoretic functions is called as arithmetic function. And let us see one example, that f of n equal to root n, where n in n. Say for example, n equal to 2, root 2 you take it. So, that is one expression. So, based on this we start with arithmetic function. F is assigned to the number root n, call it as a real number, to each positive integer n. So, because root 2 is a real number, and we have a next definition. A real function f defined on the positive integer is said to be multiplicative if f of m into f of n equal to f of mn for all m comma n in n with the GCD of m comma n equal to 1. If f of m into f of n equal to f of mn for all m comma n belongs to natural number. Now, then f is completely multiplicative. Every complete multiplicative function is a multiplicative function, and followed with the theorem. F is completely multiplicative and it is not a zero function, then f of 1 equal to 1. And the proof is, if f is not a zero function, then there exists a positive integer k such that f of k not equal to 0, hence f of k equal to f of k into 1, which is equal to f of k into f of 1, and divide both sides by f of k, we get what? F of k equal to f of k into f of 1, which is equal to what? F of 1 equal to 1. So, this way we can have the multiplicative function and it is not a zero function. And followed with the theorem, let n is equal to product of prime powers of alpha or n, that is be a prime factorization of n, then the multiplicative function f of n equal to that is product of f of pi whole power alpha I, that is n is equal to p1 into p2 into p3 and so on pk, and the powers is what? Alpha 1, alpha 2, alpha 3 and so on alpha k. If we have n, then f of n is equal to, that is f of p1 power alpha 1 into f of p2 power alpha 2 and so on f of pk power alpha k. So, this is called as what? A prime factorization of n corresponding to multiplicative function. And clearly, if k equal to 1, therefore, f of pi whole power alpha I equal to f of pi into alpha I, the first term will come. Assume that this representation is valid for n as r or fewer distinct primes, and n is equal to what? The product of I varies from 1 to r plus 1 of f of pi whole power alpha I, since the GCD of product of pi whole power alpha I is p of r plus 1 and p suffix r plus 1, then the GCD is 1, therefore, f is a multiplicative. Therefore, the proof is, you start with the definition of f of n equal to f of product of I equal to 1 to r plus 1 pi power alpha I, and then we can convert it into the base definition of f of p I alpha I comma p suffix r plus 1 to alpha n plus 1 or r plus 1. Therefore, we can split it into two ideas, that is f of n equal to f of m into f of n. So, that this can be written as f of product of I equal to 1 to r pi alpha I into f of p suffix r plus 1 alpha r plus 1. So, that we have a multiplicative, and then pi is what generalized. Therefore, each pi varies from I equal to 1 to r f of pi alpha I into f of p r plus 1 into alpha r plus 1. Therefore, by mathematical induction, I equal to 1 to r can extend to r plus 1. Hence, f of n equal to product I equal to 1 to n r plus 1 into f of pi whole power alpha I. So, f is a multiplicative, then what are all the divisors of n that you have to d divides n, and then we can write f of d, right. So, for example, n equal to 2 you take it, then g of 2 which is equal to summation, and d equal to what some number you take it 2 divides 2 of f of 2 can be written as how much, that is summation, this is 1, therefore, f of 2 is f of 2 only. So, suppose you take other than n and d, right. So, for example, you take n equal to 4 you take it, and d equal to 2 you take it, right. So, 2 divides 4 which is equal to 4 divided by 2 is 2, therefore, summation what f of 1 f of 2 is nothing but what summation running over 2 is f of 1 plus f of 2. So, this way we can express f is a multiplicative, and what are all the corresponding function of g of n, we can do that. So, so if f is a multiplicative and if g of n equal to summation d divides n f of d, where the sum is overall divises d of n, then g is also multiplicative. So, if f is multiplicative, then the greatest common divisor of two number m comma n equal to 1, then the g of m n can be written as, that is product of f of d d dash. Therefore, summation d divides m and summation d dash divide n, then f of d d dash. So, which is equal to summation d divides m f of d into summation d dash divide n into f of d dash, which is equal to g of m comma n. So, let what m is equal to 2 you take it, n equal to 3 you take it. Therefore, the GCD of 2 comma 3 equal to 1. Therefore, g of 2 into 3 is equal to what summation, that is d divides 2 and summation d dash divide 3 of f of d d dash. So, here summation d divides 2 is 2 divides 2, and then summation 3 divides 3. So, f of 3 comma 2 into 3 only will come. So, we have what we have this is 1 of f of 2, and this is 1 of f of 3, and only thing is this is g of 2 and this is g of 3. So, this way we can write g of 2 into 3 equal to g of 2 into g of 3. So, it is not directly easily do that, but only thing is we have to do with the multiplicative, we can do that. So, you can try for what m equal to 3 and n equal to 5, and you can do that. So, definitely the GCD of these two number is 1, only it is valid. So, like that we have to do for f is a multiplicative, the GCD of m comma n is 1, then we can do that. Next theorem, if f and g are multiplicative, then so as f of n equal to summation d divides m f of d into g of n by d. So, if you have n equal to what, some 5 like that, right, and then summation f of d mean that it is possible to divide that number, right, then only it is it can be expressed. So, right. So, what are all the divisors of m that you have to find out? Say for example, if 2 divides 6 like that, that is 6 divided by 2, and then f of which one is the divisor? F of 2 into g of n is 5 by 2 is, if it is possible then only we can do that, otherwise it is not possible. So, if you take n equal to 10, right, n equal to 10, then it is possible. So, do divide 6 and then we can do that. This way we can define that f of n is equal to summation f of d of g of d n divided by d. That is, the proof is very simple. If the greatest common divisor of m comma n you are equal to 1, you have to take it, and d divides mn. So, m is equal to 3 and n equal to 2, and then the GCD of m comma n is equal to GCD of 3 comma 2 equal to 1, and then you take d divides m into n. It means this implies 2 divides 6, right. It means 2, that is here d, this is d, and then d is can be expressed, that is 2 can be expressed d1 and d2, which is equal to only possible 2 into 1. Definitely the d1, that is d1 and mean 1, one of the number is 1, 1 divides 3 comma 1 divides 2. Therefore, the GCD of 1 comma 1 is 1, implies the GCD of m divides mean, what is m? 3 divides 1 and n divides, that is 2 divides 1 equal to what, GCD of 3 comma 2 equal to 1, or rather 3 divides 3 and 2 divides 2, which is equal to GCD of 1 comma 1 equal to 1. So, this way we can express f and g is a multiplicative, so we can do that. So, thus we can express f of mn equal to f of d into g of mn by d. Therefore, d can be expressed product of two numbers d1 d2, and g is mn into d1 d2. So, d1 divides m1, d2 divides n1. Therefore, this can be expressed f of d1 d2 into g of mn by d1 d2. So, d1 divides m and d2 divides n. Therefore, f of d1 and f of d2 equal to g of m divide d1 into n divided by d2. Therefore, we can shuffle like this, f of d1 into g of m1 d1 and f of d2 into g of n by d2. So, this is called as f of m and this is called as f of n. Therefore, f is multiplicative. So, this way we can prove that f is a multiplicative. Now, this very interesting one of functions of tau of 1, sigma of n and S of n. So, first we have to follow the definition. Let n be a positive integer. The arithmetic function tau of n and sigma of n are defined as follows. See, tau of n stands for what are all the divisors of n, that is called as d divides n 1, and sigma of n is what are all the divisor of n into d, some d, that it is called as sigma of n. For example, tau of n designate number of all positive divisors of n. Sigma of n designate the sum of all positive divisors of n. See the difference. Number of positive divisors, here sum of all positive divisors. So, that is most important. Let us see with some more example, right. You take n equal to 1. Now, what is tau of n? Is 1 here. Sigma of n is see number of here you have to say tau of n equal to number of all positive divisors of n, right. Say for example, here you take tau of n, number of positive divisors of 1 is 1 only, therefore, n equal to 1 is 1. Similarly, sum of all positive divisors of n is 1. Suppose you take a 2, what are all the divisors of 2? 1 and 2, therefore, totally it is 2. Here sum of the divisors of 1 is here 1, 2 also divides, therefore, 1 plus 2 equal to 3. And if you take the 2, 1 divides, 2 divides, totally how many divisors? 2, therefore, here 2, here is 3. For example, if you take 3, what are all the divisor of 3? 1 and 3. So, 1 number, 2 number, totally it is 2. And what are all the sum? So, 1 you have to add 1 plus 3 equal to 4. So, that is 4. You take example of 4, right, and then what are all the divisors of 4? 1, 2 and 4. So, how many divisors? 3, therefore, 3, and then sum them 1 plus 2 plus 4 equal to 7. So, 7. You take 5, right. So, what are all the divisors of 5? 1, 5. So, how many divisors? 2, and to sum them, that it will be 6. Now, you start with 6. What are all the divisors of 6? 1, 2, 3 and 6. So, totally 4, 1, 2, 3, 4. So, 4. Sum them 1 plus 2 plus 3 plus 6. So, 6 plus 6, 6 plus 6, 12, therefore, 12. You take a 7, what are all the divisors of 7? 1 and 7. How many divisors? 2. How many sum? It becomes 1 plus 7 is 8, 1 plus 7 is 8. So, 8 and 2. Similarly, 8 you take it 1, 2, 4, then 8, totally 4, 1, 2, 3, 4. So, 4. What are all the sum? 1 plus 2 plus 4 plus 8 equal to what? 15. So, 15 coming. Similarly, for 9 you have 1, 3 and then 9, totally 3, 1, 2, 3. So, 3. What are the sum? 1 plus 3 is 4, 4 plus 9 is 13. So, 13. For 10, we have the possibilities of divisor is 1, 2 and then 5 and then 10, totally 4. So, 4. how many sum them? 1 plus 2 plus 5 plus 10, which is equal to what? 15 plus 2 is 17 plus 1 is 18. So, 18. Similarly, 100 you take it, 100 you take it, 1 divide, 2 divide, 3 does not divide, 4 does not divide, 5 divide, and then 6 does not divide, 7 does not divide, 8 does not divide, 9 does not divide, 10 divides, and then 11 not divide, 12 not divide, 13 not divide, 14 not divide, it means exactly should divide, 15 not divide, 16 no, 17 no, 18 no, 19 no, 20 will come, right. Next to 20, 25 will divide, next 50 will divide, right, and then 100 will divide. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 9. Add them 100, 150, 175, 195, 95, 2000, 5, 10, 10 plus 7, 2017, superbly coming. So, this way we can write tau of n and sigma of n. So, the same way we can do 101, only 2 term 1 and 101, add them 102 will come, 220 is 12, 504, 284, 6 and 507. So, this way we can find out tau of n and sigma of n. Similarly, we can do for what n be a positive integer, s of n is nothing but sigma of n minus n. So, we have by definition 1.543 and 1.44 we have sigma of n we know. What is sigma of 1? So, s of n, s of 1 means sigma of 1 minus 1, sigma of 1 is 1, 1 minus 1 is 0, therefore, 0 will come. And then s of 2 you take it is sigma of 2 minus 2, which is sigma of 2 is 3, 3 minus 2 which is equal to 1, so 1 will come. If you have s of 100, then sigma of 100 minus 2, what is sigma of 100 which is equal to 217 minus n. What is n? Sorry, here n is 100. 100 means, so 117. So, 117 will come. So, like that you may check s of 220 which is equal to sigma of 220 minus 220. So, sigma of 220 is 504 minus 220. So, which is equal to 4 minus 0 4, 10 minus 2 is 8 and 4 minus 2 is 2, 284, 284 is coming. So, this way we can express what s of n. So, this is the meaning of tau of n, sigma of n and s of n. Next we have n be a positive integer which is greater than 1 and n can be written as product of prime powers. Then the positive divisors of n are precisely those integer d of the form, and d is equal to product of prime powers which is beta I lies between 0 to alpha I, and then we can express what the function like this. So, if d divides n, that is n can be expressed d into some numbers, by fundamental theorem of arithmetic, the product of prime factors of unique way we can write. Therefore, the prime numbers is in the factorization D occurs in Pj. Further, the prime beta j of Pj is occurring the prime factorization. D cannot be greater than alpha j. Therefore, beta j less than or equal to alpha j. Conversely, beta j less than or equal to alpha j, D clearly divides n. So, this way we can express what the function. Next, let n be a positive integer, then tau of n is also multiplicative. Tau of n is what are all the divisors of n, you take it, and then if what to product them, that is see we already taken 6, what are all the divisors of 6, 1 and 2 and 3, 4, totally tau of 6 equal to 4, right, and then now we have 3, you take it. So, it becomes 1 and 3, therefore, tau of 3 equal to 2 and 2 you take it 1 and 2. So, tau of 2 equal to 2. Now, tau of what 6 is written as tau of 2 into tau of 3. Then we have what tau of 2 is 2 into 2, which is equal to 4. Tau of 6 is also a 4, therefore, it satisfies. Therefore, tau of mn equal to tau of m into tau of n, that is the first statement. If n is a prime, say p, then tau of p equal to 2. More generally, n is a prime power of p power alpha, then tau of p power alpha equal to alpha plus 1. If n is a composite and has a standard prime factorization form, then tau of n equal to alpha 1 plus 1 into alpha 2 plus 1 into alpha k plus 1, which is equal to product of I equal to 1 to k alpha I plus 1. For this case, if for second case, if n is a prime, then tau of p equal to 2 only. For example, you take 2 n equal to 2 is a prime, and what is tau of 2? Tau of 2 is 2 already found out, therefore, 2 then it satisfies. If n is a prime power of p power alpha, say for example, you take a 4, right, then it becomes 2 square, right, then tau of 2 square is equal to the 2 plus 1, right. So, what happened? Tau of p power 2, n is a prime, then power p power alpha is what 2 square, then what happened? Alpha plus 1 is 3, that is we can write, say what is 2 square? 2 square is a 4, sorry, correct, coming. So, so we have tau of 4, right, 4 you take it, 1, 2, 4, see totally it will come 3, total number is 3, therefore, here 2 square is also 3, therefore, it works, beautifully it works, right. If n is composite, right, if n is composite mean n equal to say n equal to 6 you take it composite. So, what you have to do, it becomes 2 into 3, n is a composite and standard prime factorization form is it becomes 2 power 1 into 3 power 1. So, tau of 6 you take it. So, what happened? 1 plus 1, right, that is alpha 1 plus 1. right, into alpha plus 1 is 1 plus 1. Therefore, only two things will come. Therefore, 2 into 2 equal to 4. Therefore, tau of 6 equal to what, 4. So, it satisfies. So, this way we can express tau of n is a multiplicative prime factorization. So, keep it in mind this, right. We will go to the proof of this theorem. Since the function is a constant function, therefore, f of n equal to 1, that is, therefore, it folds, and then tau of n equal to summation d divides n 1. The result follows immediately from the theorem 1.43, that is explained clearly. Clearly, if n is a prime, there are only two divisors, namely 1 and n itself. If n equal to p power alpha by lemma, the positive divisor of n are precisely those integer of d equal to p power beta, where beta lies between 0 to alpha, and there are alpha plus 1 choices for the exponent beta, and there are alpha plus 1 possible positive divisors of n. So, according to the lemma 1.41, and there are alpha 1 plus 1 choices for the exponent beta 1, alpha 2 plus 1 choices for the exponent beta 2, and so on, alpha k plus 1 choices of the exponent beta k. Therefore, the multiplicative principle, it follows that there are alpha 1 plus 1, alpha 2 plus 1, and so on, alpha k plus 1 is different choices for beta 1, beta 2, and so on, beta k. Thus, there are many divisors of n. Therefore, tau of n equal to alpha 1 plus 1 into alpha 2 plus 1, and so on, alpha k plus 1. Now, the theorem, the product of all divisors of n is product of d divides n into d equal to n power tau of n by 2. That is, you take n equal to 2, right, tau of 2 is 1 and 2, that is totally 2 divisors. Therefore, 2 power 2 by 2, which is equal to 1. Therefore, if you divides d, that is, you take n is 2, how many divisors of n? 1, of d is only 1, satisfies. So, like that we have to do the product of all divisors. So, let d denote the arbitrary positive divisors of n, so that n can be written as product of divisors. Say for example, take 6, 2 into 3, let it be d and d dash. Now, for some d dash, d ranges over all of tau of n, right, the positive divisors of n. There are tau of n such a equation, and multiply these together, we get what, the 2 divides, right, this corresponding product of d divides n into d, and product of d dash divides n d dash, therefore, which is n power tau of n, where d runs through the divisors of n. So, that d dash equal to what, how many divisors of this and this one are also equal to one another. Therefore, n power tau of n is equal to, we together product of d divides n into d dash whole square. Therefore, it is equivalently n power tau of n divides 2 equal to product of d divides n into d dash. Next, we have a theorem, let n be a positive integer and sigma of n is a multiplicative. Therefore, sigma of mn is equal to sigma of m into sigma of n. So, we have n is a positive integer, say n equal to 6. Therefore, n can be written as 2 into 3. Therefore, sigma of 6 equal to sigma of 2 into sigma of 3, and sum of the divisors of 2. So, 2 as a divisor 1 plus 2 is equal to 3. Therefore, it becomes 3, and and this one as 6 you take it, 6 what are all the divisors, right. Say we have what 1, 2 and 3 and 6. So, we have 12 and then you have to take a 3 as divisors of what are all the divisors 1 and 3. If you add, it becomes 4. So, it becomes 3 into 4, which is equal to 12, and a 6 having the 12. So, we have sigma of 6 equal to 12 and sigma 2 into sigma 3 is a 12, therefore, it satisfies. So, like that we have to do for n is any positive integer, it works. If n is a prime, say p, then sigma of p equal to p plus 1. For example, if you take, so this is what sigma of 2. So, if n equal to 2 and then sigma of 2 equal to what are all the primes of this one is, so sigma of 2 equal to 2 plus 1 equal to 3. So, beautifully it comes. So, sigma of p equal to 2 plus 1. More generally, if say take 4 what are all the divisor 1, 2, 4. So, sum them, it becomes 7. So, sigma of 2 square equal to 2 power what 2 power 2 plus 1 minus 1 by 2 minus 1, which is equal to 2 cube minus 1 by 2 minus 1, which is equal to 8 minus 1, 7 by 1 equal to 7, and beautifully it works. So, this way we can write what the more general form of, if n is prime, say p, then sigma of p equal to p plus 1. More generally, if n is a prime power of p power alpha, then sigma of p power alpha equal to p power alpha plus 1 minus 1 by p minus 1. Now, we have to go to the n is a composite and standard prime factorization form, then sigma of n equal to p 1 power alpha plus alpha 1 plus 1 minus 1, p 2 power alpha 2 plus 1 minus 1, and p k power alpha k plus 1 minus 1, and divided by p 1 minus 1, p 2 minus 1, p k minus 1. We can write like that. Say you have to take n is a composite, mean n equal to 6, right. So, n can be written as 2 into 3, right, and 2 power 1 and 3 power 1. So, sigma of 6 you take it, it becomes 12, already we discussed, right. Now, you can write sigma of 6 is equal to p 1. What is p 1? 2 power 1 plus 1, 2 power 1 plus 1 minus 1 by 2 minus 1 into 2 power 3 power 1 plus 1, because power is 1 minus 1 by 3 minus 1. So, 2 square minus 1 by 1 into 3 square minus 1 by 1, 2. So, 3 minus 1 is 2, 2 minus 1 is 2, therefore, what 4 minus 1 by 1 into 9 minus 1 by 2, which is equal to 3, which is equal to 8 by 2 equal to 4, 3 into 4 equal to 12, and beautifully it works. So, in general we can write the product of I equal to 1 to k pi alpha I plus 1 minus 1 by pi minus 1, like that. So, this is a way we can write what sigma of n. Now, we have a proof. The result follows immediately from theorem 1.43, since the identity of the function f of n, where sigma of can be represented in the form of sigma of n equal to summation d divides n into d, So, this way we can express the first theorem proof. For second theorem, the divisor of p power alpha or a, whatever it may be, are 1, p, p square and so on, p power a minus 1 and so on, p power a. Consequently, p power a is exactly a plus 1 divisors start from 1, and tau of p power a is a plus 1. Also, we note that sigma of p power a is all the sum you take it, which is a geometric progression, and then a into a is 1 into r power a into r power n minus 1 by r power minus 1 by r minus 1. Here totally n plus 1 term, therefore a is 1 into here r is a p power here this is p square p into p power what n is what a plus 1 term minus 1 by p minus 1. So, hence we can easily prove by method of geometric progression, and it follows the mathematical inductions of the general term. So, we use the theorem 1.1 so that we can get the proof of second. For example, you take sigma of phi cube. Phi cube is 5 into 5 into 5, that is 25 into 5, which is equal to 125. So, this can be written as what? That is sigma of phi cube as per the second theorem statement 1 plus phi square plus phi cube. So, it is geometric progression with a first term a equal to 1 and r equal to 5. Therefore, 1 into r power, that is phi power r plus 1, r is equal to n is 3 plus 1 minus 1 by what 5 minus 1, which is equal to 5 power 4 minus 1 by 4, which is equal to what 25 into 25 minus 1 by 4, which is equal to 156. Therefore, it follows from that. Another way is tau of phi cube can be written as that is a plus 1, that is 3 plus 1, which is equal to 4. So, this way we can write the what number of factors and sum of the divisors, number of the divisors and sum of the divisors. So, this way we can express the proof of 2. Now, we have a proof of 3. Sum of the divisors of the positive integer is n equal to p1 power alpha 1, p2 power alpha 2 and so on, pk power alpha power k can be expressed by the product of 1 plus p1 square and so on, p1 power alpha n into 1 plus p2 and p2 square 1 plus p2 plus p2 square and so on, p2 power alpha 2 and so on, 1 plus pk square and so on, pk power alpha k. So, using the finite geometric series of sum of the terms 1 plus x square into x power n is x power n plus 1 minus 1 by x minus 1. Therefore, by simplifying the k sums, the sum of the product to find the sum of the divisors can be expressed as sigma f n equal to p1 power alpha 1 plus 1 minus 1 by p1 minus 1, p2 power alpha 2 plus 1 minus 1 by p2 minus 1 and so on, pk power alpha k plus 1 minus 1 by pk minus 1. So, we can write the general term as product of what this expression as like this. This is a symbol for product of each ratios. I varies from 1 to n, 1 to k. So, this way we can express the what sigma of n, tau of n and s of n.